Hello everyone, myself Rupalakshmi K, student of Computer Science Department at Sri Venkateswara College of Engineering. In this video, I'll be talking for a research paper in the field of big data for the subject Big Data Analytics. These are the contents discussed in the video. Research paper introduction. The title of the paper that I'll be discussing is Correlation Expert Tuning Systems for Performance Acceleration. In this paper, there are 6 authors which have been listed here, and the paper was published on 2nd September 2022. Statement. Database performance tuning is complex due to the numerous configuration knobs in the modern databases like MySQL and PostgreSQL, each having over 200 knobs. This complexity makes it difficult for users and database administrators to find optimal configurations for specific workloads. Current auto-tuning methods often rely on excessive offline training and trial and error approaches, leading to inefficiencies. Many systems offer only coarse-grained tuning, overlooking the diverse nature of workloads and the varying importance of knobs, which results in suboptimal performance. The most time-consuming part of the process is the performance measurements needed to obtain reward values, creating a zero knowledge scenario. Thus, integrating expert knowledge and correlation rules is essential to enhance the tuning process, reduce training cost, and improve overall efficiency in database optimization. Objectives of CX tuning. CX tuning is a system designed to integrate expert knowledge into the database auto-tuning process. It identifies and utilizes relationships between various configurations knobs to make more informed tuning decisions. Expert knowledge module. The system includes both external and internal expert rules. External expert rules use a multi-instance mechanism to classify workloads and recommend optimized knobs for specific scenarios. Internal expert tool capture learned correlations between knobs to better understand how configurations interact. Correlation rules. These rules help filter out ineffective knob combinations, focusing on those that are likely to improve the performance based on past data and expert insights. Utilize reinforcement learning for efficient auto-tuning. Reinforcement learning framework. The RL model adapts tuning strategies over time, optimizing knob selections to match the workload needs and performance goals. Dynamic adaptation. CX tuning adjusts recommendations in response to the changing workloads, ensuring ongoing database optimization. Reduction of trial and error. RL minimizes unnecessary performance evaluations by learning from past experience, reducing inefficiency. Reduce training time and improve performance efficiency. By incorporating expert knowledge, CX tuning skips ineffective knob evaluations, speeding up tuning. Faster convergence. Expert rules help the RL algorithm find optimal configurations quickly. Enhance performance. The system aims for improved through output, lower latency, and better resource utilization. Overview of CX tuning. CX tuning is a sophisticated system for auto-tuning databases consisting of three primary modules. External expert rules module, purpose, classifies workloads and recommends high performance configuration knobs based on external expert knowledge. Multi-instance mechanism, categorize workloads to identify relevant knobs for specific scenarios. Recommendation system provides optimized configurations to enhance tuning. Internal expert rules module. Purpose integrates a learned expert knowledge and analyzes the correlation between knobs. Correlation rules model captures relationships between knobs to reduce the tuning search space. Knob consistent rules guides tuning within the system resource limits. Internal expert rules module purpose integrates a learned expert knowledge and analyzes the correlation between knobs. Correlation rules model captures relationships between knobs to reduce the tuning search space. Knob consistent rule guides tuning within system resource limits. Working mechanism for CX tuning. CX tuning's working mechanism involves a systematic iterative process to optimize database performance through expert knowledge and reinforcement learning. Classify workloads uses the external expert rules module to classify workloads based on their characteristics, employing a multi-instance mechanism. Purpose is tailors tuning to each workload type for better performance, utilizes expert knowledge to inform tuning recommendations. Recommended optimal knobs recommends high performance configuration knobs based on workload classification, focuses on relevant knobs likely to improve performance, filtering out less effective options. Train using internal expert rules. The auto-tuning module trains the RL algorithm using insights from the internal expert rules module, provides correlation rules and constraints to guide training, speed up the tuning process by avoiding ineffective knob combinations. The system refines its tuning strategies in an iterative feedback loop, continuously improving and adapting to changing workloads. Multi-instance mechanism in CX tuning. Fine-grained workload classification. Multi-instance mechanism classifies workloads with detailed precision, considering factors like read or write ratios and transactions types. This allows for tailored tuning to meet the specific needs of each workload. Dynamic high-performance knob recommendations. Multi-instance mechanism dynamically adjusts configuration knob recommendations based on real-time workload changes. It focuses on high-performance knobs to maintain optimal performance. Reinforcement learning in CX tuning. Core algorithm. RL is the foundational algorithm balancing exploration, trying new configurations, and exploitation, improving known configurations. Learning from feedback. RL uses performance feedback to optimize knob selection over time, continuously refining recommendations for higher throughput and lower latency. It adapts to changing workloads, ensuring effective tuning. Correlation expert knowledge model in CX tuning identifies knob relationships, analyzes interdependencies among configuration knobs, allowing for guided tuning that accounts for the knob influencing each other, ensures a holistic tuning to avoid suboptimal configurations, reduces search space, recognizes knob correlations, narrowing down the tuning options to focus on promising configurations, enhances tuning efficiency by speeding up the process and reducing computational overhead. Tuning acceleration in CX tuning skips unnecessary measurements, uses correlation rules to skip irrelevant knob combinations, saving time and resources, prioritize configurations likely to positively impact performance, informed decision making, incorporates expert knowledge to make a readable knob adjustments, adapts tuning strategies based on past performance data and best practices. Comparison with existing models. CX tuning addresses the limitations of existing auto-tuning methods like best configuration, time-consuming searches, and his heavy reliance on historical data. Auto-tuning depends on high-quality samples, which may be scarce. CDB-Tune suffers from long training times and coarse-grained tuning. CX tuning's advantages: reduces training time by skipping unnecessary evaluations, provides fine-grained dynamic tuning throughout expert knowledges, and MIM adapts to changing workloads for better performance optimization. Experimental results: training time reduction. CX tuning reduced training time by 67.77% to 77.67 compared to CBD tune. Performance gains achieved up to 61.73 through output improvement and up to 63.45 latency reduction across various workloads. Conclusion: CX tuning represents a significant advancement in the field of database auto-tuning by effectively reducing training time while enhancing overall performance. The system successfully combines reinforcement learning with expert knowledge, allowing for optimal tuning of database configurations. This integration not only streamlines the tuning process but also ensures that the recommendations are tailored to specific workloads, leading to improved efficiency and performance outcomes. The experimental results demonstrate that CX tuning outperforms existing methods, making it a valuable tool for database administrators seeking to optimize their systems. Future works: several potential enhancements could further strengthen CX tuning's capabilities. Algorithms refinement: refining the reinforcement learning algorithms could enhance CX tuning's adaptability and responsiveness through dynamic workload changes. Broader expert knowledge: expanding the system's expert knowledge base could improve its adaptability to handle wider range of configurations and scenarios. Additional workload testing: testing CX tunings across a broader variety of workloads from different application domains could demonstrate its robustness and versatility. Diverse configuration: exploring more database configurations um, and tuning knobs may help identifying optimal settings for different environments, expanding CX tuning's applicability. These enhancements will allow CX tuning to stay relevant and effective in the evolving landscapes of database management and optimization. Thank you.